Not time to sleep. Right, I know I've received tons of emails about the ARC coursework, so I'd like to tell you some more hints. I mean, I already sent you 2 or 3 emails about the ARC coursework, right? I assume that all of you know how to read the data, and all of you know how to compute the log returns, right? I assume all of you know that, how to do it. Now, when it comes to fitting a distribution to the log returns, you need to use the package fit right, you need to use the package. There's a package called fitdist-r+, right? And you need to download the package in order to fit distributions. And I told you how to do that, how to download the package. So you use these 2 commands: install and then you use the command library, L-I-B-R-A, library, the same thing, fit. Right? If you use these 2 commands, that means that you have installed the package fitdist-r+ to the working environment, right? And there's a command. All right, this is how you install the package. Now, to fit distributions, you need to use there is a command in the package. I mean, the package has several commands. I mean, you can look at the manual file for the package. It has a list of different commands. One of the commands is called fitdist, F-I-T-D-I-S-T, right? And this command will allow you to fit distributions. So, for example, suppose you want to fit the normal distribution. If you want to fit the normal distribution, you will say fit dist x. X will contain x is the object that will contain the log returns you already read before. And then in quotes, double quote, you will say norm. Norm is the distribution that you want to fit, right? And close bracket. So this command will fit okay. This command will fit the normal distribution to the log returns, right? Now, suppose you want to fit some other distribution, say, for instance, the student's t distribution, which is one distribution I talked about in the class. You will use this, so to student, because the student t, I mean, for certain distributions, is not implemented in the package, you need to specify the starting values. So you need to say start value, you need to use the command start list, this is L-I-S-T, list df equal to 1. Now what this means is that it tells the computer that you are trying to fit the student t distribution with the initial value of df, or degrees of freedom, equal to 1. It doesn't need to be 1. It can be 2, 3, 100 million, etc. But it's just an initial value, just to start the algorithm to fit the distribution students t, right? Okay, so this will fit okay, and so on. So these, and there, so practically using the command fit dist, you can practically fit any distribution, right? But because, I mean, there are millions of distributions, so I don't want you to, maybe take your lifetime. It will take your lifetime to fit millions of distributions. To make things easier for you, I mean, I think I mentioned this to some of you. The distribution that will give a good fit to the data is one I have talked about in this class. Of course, I can't tell you what that is. I mean, it's a distribution that I talked about during my lectures. Okay, so I've taken the liberty right? I just want to list, I know you guys know where the scan nodes is, right? I just want to list you all the distributions I have talked about in my notes, right? Number 1, normal. Number 2, binomial. Number 3, chi-square. Can you see this, guys? Number 3, chi-square. Number 4, t, students t. Number 5, scales t. Number 6, uniform. Number 7, Poisson, exponential. Geometric, Pareto, log normal, Laplace. Listen, guys. These are distributions I mentioned in my lectures so far, right? And what I'm telling you is that one of these, or at least one of these distributions will provide a good fit. When I say good fit, I will explain what I mean by that in a minute, to the data set that I gave you, right? Of course, I can't tell you which one it is, because then I will give away the answer. So all you need to do is to try all of these, right, and find the one which provides a good fit, right? Okay, it's not a difficult job, is it, guys? It shouldn't take you a million years to do that. So now, when it comes to right, let me put this over here so you can see. Oh man. Right, these are the distributions. When it comes to checking the goodness of fit, all right, when it comes to checking the goodness of fit of the fitted distribution, you need to use a command called KS test. KS stands for Kolmogorov-Smirnov. This is the most powerful test in statistics to check for goodness of fit of a model, right? Okay, if it says that, if it gives a p-value that is less than 0.05, that means the model does not give a good fit. So for example, So some examples are as follows. So if you say, right, if you use this command, right, what it does, it performs the goodness of fit test on the fitted normal distribution, which you already fitted here. Right, this is how you fitted the normal distribution. And when you fitted this distribution, it gives you two estimates, one for the mean and one for the standard deviation. So you need to put the estimates here and here, right? So if you execute this command, it will give you a p-value. And if the p-value is less than 0.05, that means it's not a good fit, right? So for example, to test the t distribution, which we fitted here, you will use this command here, x, comma, in brackets pt, comma, df. df is the degree of freedom estimate given by this command here, right? So the idea is that if the p-value returned by these commands, if p-value is greater than 0.05, then you can assume the model or the distribution all right? Okay, guys. So this is all you need to do, guys. I'm not asking you to do a difficult job because there are only this many distributions you need to try, and at least one of them will provide a good fit. So all you have to do is just try them and see which one it gives a good fit. Is that okay? You have any questions, guys? Anyone has any questions? And so the coursework is due in exactly 1 month time, the 29th of April. So you should hand it in person. I mean, I will be here during the Easter break. So there's no excuse for saying I'm not in, so therefore you are not able to hand it. All right? So please give it to me in hard copy form. Either you can write it in either Word or LaTeX, or if you prefer, you can write it by hand, right? Either way, okay, just give it to me in hard copy form by 29th of April, 3 p.m., right? Oh, is that okay, guys? Any questions you guys have? I mean, you are most welcome. I mean, you are most welcome to email me 24/7 or Zoom me 24/7 if you have questions about the art coursework or any other question, all right? Okay. All right, now before I go ahead, all right, on Monday this week, I talked about confidence intervals for 2 sample problems. So I just want to summarize what I did on Monday, right? And then I will. So this is confidence interval for 2 sample problems. And there are 4 confidence intervals I talked about. The first one for the difference in population means when the variances are known, right? And it turns out that in this case, the confidence interval is given by this formula here, right? Okay, guys? Now, the second I talked about is this one. It's the confidence interval for the differences in the population mean when the variances are unknown but equal. The variances of the 2 populations are unknown, but they are equal to each other. In this case, I know the mathematics got pretty nasty, you probably remember from Monday. After some nasty mathematics, which you don't need to know, this is what the confidence interval you get, right, for the differences in the two population means, right? That's number 2. Now, number three is this one. This is the confidence interval for the difference in the two population means when the variances are unknown and not equal. And in this case, you get this as the confidence interval. As you can see, it's pretty nasty looking. Okay? Okay. And finally, this is number 4. This is the confidence interval for the difference in proportions. So when you have two Bernoulli populations with parameters P1 and P2, you're looking for the confidence interval for the difference, P1 minus P2. And it's given by this formula here, right? And as I said on Monday, you don't need to know the derivations for any of these. You don't need to know the derivations for any of the two sample confidence intervals. But you will need to know the derivations for the one sample confidence intervals, right? Okay, guys. Now one thing I promised you guys is that I will do 10 examples on every concept I talk about. So in the 45 minutes I have, I will try to do 10 examples. Example 1. Right. So example 1 is this. You have a random sample from a normal distribution with mean equal to theta, the variance equal to 1. We want to find a confidence interval for theta, right? So where do we start? The first thing you must note is that the x bar will have a normal distribution with parameters Yes, this is a formula I mentioned many times. So x bar minus theta will have a normal distribution with parameters 0 and 1 over n. Okay? So x bar minus theta divided by 1 by root of n will have the standard normal distribution. This is, another way of writing this is root of n all right. Right. Now, to find the confidence interval, yeah, you remember, because this guy has a standard normal distribution, we can say the probability equal to, can you tell me what is this equal to, guys? Tell me. 1 minus alpha, right? So this implies this, right? And the next step is to rearrange this as a statement on theta. I'm sure all of you know how to do that. So this becomes, as a statement on theta, you get this x bar minus x bar plus okay. Are you with me? So hence the conclusion is the following. Hence 100 times 1 minus alpha is the following. Yeah. You guys okay with this? So this is pretty straightforward, right? So this is an example on, yeah. Have any questions on this? You okay? So that's example 1. We've got 9 more to go. Example 2. Example 2 is the following, right? Suppose so here we have a random sample from a normal distribution with 0 mean and variance sigma squared, and we want to find a confidence interval for theta. Right. This is where what we learned before comes in. Do you guys remember? Okay, I'm going to test your memory. I'll be disappointed if you don't know what it is. Do you guys remember the distribution of this? What distribution does this have? This is something we did long time ago. You forgot? Anyone wants to have a try? Come on, guys. Are you looking forward to the Easter or what? Yeah? This has a chi-square distribution with n degree of freedom. Do you remember this or not? Yes? Okay. So what this implies is that okay, and this implies that the probability that Yes. All right, now rearranging this, if you rearrange this as a statement on theta squared, you will get the following. Yeah, you see what I've done? I have rearranged this as a statement on theta squared, right? Now what we are looking for is the confidence interval for theta. So what you need to do next is to take the square root. Okay, are you with me? I've taken the square root because we are looking for a confidence interval for theta, not theta squared, right? Right, so hence, the conclusion is the following. Hence, okay, so this is the answer to example 2. Yeah, do you follow? Any questions you have? Right? Yes, no? Feel free, if you have any questions, do let me know, guys. I mean, right, number 3. This one is a little bit tricky, so I'm going to example. Right. So here you have, this is a little different from the others. You have a random sample with the CDF x divided by a squared. X lies between 0 and a. And we want to find a confidence interval for a. Now, in this case, right, you won't be able to do this without a hint. So, right, so let Z denote the maximum of x1 to xn. Right? Okay, if the maximum is less than equal to Z, then each of these guys has to be less than Z. Right? Now, because these are independent random variables, you can write this as by independence, right? And we are told the CDF for each of these. This is the CDF of x1, which is Z divided by a squared so what you have is Z divided by a to the power 2n. Okay? All right, guys. So that's the CDF of Z, right? Now, if we want 100 times 1 minus alpha percentile. So we need to, from the CDF, you can work out, you can work out the points that corresponds to the areas alpha by 2 and 1 minus alpha by 2. What I mean is the following. Let me show you what I mean. I'm not good in drawing, as you know already. Suppose this is 0. Suppose this is A. Suppose this is 1. And suppose this is 0. So what I'm gonna draw is I'm gonna draw a picture of the CDF fz versus z. Which is this function here, right? So if you plot this function versus z, it will look something like this. Excuse me for my inability to draw. It will look the graph of this versus z will look something like, it will look something like this, right? Okay, so I plotted this versus z. Now to figure out the confidence interval, we need to find 2 points, right, corresponding to alpha by 2, so, and 1 minus alpha by 2. So let's take this point and this point, right? And we want this area here, to be to be equal to alpha by 2, right? And we also want the area here. Sorry. We also want the area here to be alpha by 2. So the middle area, the area between them, will be 1 minus alpha. So this is 1 minus alpha, this is alpha by 2, this is alpha by 2. Now, based on this picture, you should be able to figure out what these 2 points are, right? So let's take this point first. To determine this point, right, what you're looking is right, which implies that z is equal to a times alpha by 2 power 1 over 2n, right? And looking at this point, you have z divided by a power 2n is equal to 1 minus alpha by 2. So z is equal to a times 1 minus alpha by 2 to the power 1 over 2n. I don't know whether you got what I'm doing. I'm trying to determine 2 points on the x-axis, so the area between them is equal to 1 minus alpha. Now this point, to determine the value of this point, you need to set the CDF equal to alpha by 2, which is this area. And to determine the value of this point, you need to set the CDF equal to 1 minus alpha by 2, because this area is alpha by 2. So the area to the left is 1 minus alpha by 2. And that gives you z equal to this, right? And so this implies that the probability that right? The probability that you are between these 2 points, this point and the probability that you are between these 2 points is equal to 1 minus alpha, right? So in other words, the probability that okay, right? And now if you arrange this, because we are looking for a confidence interval for A. So if you rearrange this as a statement on A, this is what you will get. You will get yeah. Are you with me, guys, or not? Or you lost? Yeah? You're right, sir. Okay. All right. So hence, the conclusion is the following. Hence, So this is the answer to example number 3. Yeah? I know this is a little different from the 2 previous examples I did, right? So here you had to first derive the CDF of Z, right? And draw the picture of the CDF, right? And then find the 2 points, and between which the area is 1 minus alpha, right? And once you've done that, you're done, right? Okay. Right. So that's example 3. Now, example the next example, example 4. Yeah. So we have a random sample from a log normal distribution, and we want to find the confidence interval for theta. Now, I don't know whether you know that, I mean, if you had looked at the list of distributions I gave on the first day, one of the things you will notice is the following. If xi has a log normal distribution with parameter theta and 1, then log of xi will have the normal distribution with parameters theta and 1. Do you know this fact? I mean, you might have learned this in probability 1, I don't know. Did you guys learn this in probability 1? No? All right. Anyway, this is one of the properties of the log normal. I think it's in the list of distributions I gave you at the beginning of the lecture of the course, right? So what this implies is that if log of xi has a normal distribution, then the average should also have a normal distribution with these parameters, okay? Right, and so the difference minus theta should have a normal distribution with parameters 0 and 1 over n. Okay? And finally, you should divide this by 1 over root of n. Yeah? They should have a standard normal distribution, right? Okay, so what I'm saying is the following. I'm saying that root of n multiplied by should have this, right? Now, using this fact, we can write down the following statement. We can write down that the probability that can write this like this, yes? Now rearranging this, let me put this over here. Rearranging this, you can get a statement on theta, and that's all you need to do. So rearranging this, you get the following. Right. Okay, and one more time. Okay, putting this as a statement on theta, you will get the following. You will get um, 1 over n times the sum of log of xi minus 1 over root of n then plus equal to 1 minus alpha. Right? So hence, hence 100 times 1 minus alpha confidence interval for theta is what I have written down. So the lower limit will be this is the lower limit of the confidence interval, and the upper limit is the upper limit. All right. Now, unfortunately, I've had time to do only 4, so I don't know. I will do more examples during the revision week. But before you go, next week, the topic for the course will be test. All right, this is the topic for next week. And also, if you haven't been to the example classes this week, can you come to the one today from 1 to 2 in G209 and 2 to 3 in G207? All right, that is if you haven't been to any of the example classes so far this week. All right, please do.